When we look out into the vast, expansive, awe-inspiring cosmos, there are innumerable stars out there. Yet, one of them dominates our sky and our lives, burning brightly and ferociously at the center of our solar system, the Sun. It's easy to see how generations of humans before us were inspired to create all kinds of legends to explain its mesmerizing glow. Now, as technology has advanced beyond the realms of their wildest imaginations, we can delve into the processes within and around our neighboring yellow dwarf, going deeper than ever before. As we journey through its ferocious atmosphere, let's explore what I'm sure you'll agree are the fascinating phenomena that materialize there. I'm Alex McColgan and you're watching Astrum, and in this video I want to dive into the Sun, drawing on different wavelengths of electromagnetic energy to showcase the star in a new light. Previously, we've explored Jupiter and some of its moons through the lens of the electromagnetic spectrum, which you can see in this video here. Today, we will be revisiting this approach, but this time, rather than a planet, it'll be adapted to investigate a highly energetic ball of plasma. The light we'll be looking at is old. Although light is the fastest thing we know, the image of the Sun that we see from Earth is approximately 8 minutes and 20 seconds old, meaning we are viewing what the Sun looked like a few minutes in the past. And if you count how long it takes the photons generated within the Sun's core to make their way through each layer of the Sun before escaping into space, the light that reaches us is anywhere from 10,000 to 170,000 years old. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the Sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA space mission launched back in February 2010. SDO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the Sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the Sun's corona. Interestingly, the Sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the moon is perfectly aligned between the Earth and the Sun for a fleeting period of time, the view of the central, brighter disk, known as the photosphere, is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the SDO. This makes it a useful tool for scientists' studies. But let's go a little deeper, to features of the Sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions where the Sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the Sun itself, from which the fields ultimately originate. But they are not the only feature of the Sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the Sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with Earth's magnetosphere, beautiful auroral lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the sun's outer layers to look at. There are solar filaments, known as solar prominences, the large loops of plasma that rise from the sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of kilometers into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a solar prominence snakes its way out of the photosphere and into the sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the sun's intense magnetic fields are causing this material to move. One fact you might not know about the sun's atmosphere is that it sometimes rains there. Not all of the charged plasma fired into the sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled until it falls back to the sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the sun's surface is only the fate of some of the sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band firing into space. On the sun, thanks to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the sun for some time, before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the SDO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the sun, alternating around an 11-year solar cycle, which I did a video about here. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same time period, the following two images use different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the sun's atmosphere yet. Moving further inwards, let's look at another image produced by the SDO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 degrees Celsius or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the Sun's chromosphere, which is the last layer of atmosphere before we reach the Sun's surface itself. Imaged here, using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the Sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 5 to 10 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the Sun's magnetic fields at that level. That is, until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the Sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy they needed to escape the Sun's plasma and shoot up into spicules. Descending further through the Sun's lower atmosphere, we eventually reach the photosphere, the surface of the Sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the Sun is. The Sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the Sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the Sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the Sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now, let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth, and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell, before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 kilometers per second, generating waves on the sun's surface due to sonic booms. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think this image looks quite grainy for such a high-tech space probe, and you're right, it does. But that graininess is the granules on the photosphere of the sun, not a processing effect or excess noise in the image. And that's it. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun, using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery. But we can see the benefits of using light of all different spectrums in our study of the sun. They help us observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and shape-shifting cells, just to name a few, in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Maybe one day we'll find ways to see deeper, using techniques we can barely dream of currently, just like those ancient generations of humans long ago could hardly dream of the methods we're utilizing these days. But for now, just knowing there is so much going on unseen in the universe, and knowing we have the means to uncover it, fills me with excitement and curiosity. Who knows what else might be out there, waiting to be found. If I were to tell you that the cycles of the sun could affect your entire life, you might think that I was suddenly taking a turn away from astronomy and into astrology. While there are many people in the world who believe that you can learn things about your future by studying the position of stars and planets, it's not a position I tend to take on this channel. I'm more interested in the beauty of space and the mechanisms that explain why it is the way it is. But sometimes there is a grain of truth behind even the most surprising of stories. So allow me to put on my prophesying hat. While I'm no writer of horoscopes, I will predict that based on the current state of the sun, over the next few years, you might be more likely to experience bad health, less reliable technology, see warmer weather with fewer clouds, and possibly could be influenced in other surprising ways. How do I know? Because it turns out the sun, that giant ball of fire in our sky, is not just the place we get our energy from. Science is starting to show that its 11-year cycles might just be the metronome measuring out how life on our planet tick, tick, ticks. I'm Alex McColgan, and you're watching Astrum. Today we're going to look at sun cycles. In particular, I intend to show you exactly how the cycles of the sun are already influencing the course of your life. It's no surprise that the sun is influential to life on Earth. After all, in many respects, it is life's origin. Life on Earth needs energy to function, and the sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our sun. But beyond the gift of that life-sustaining energy, it's easy to think of the sun as fairly static. We see it rise and fall in the sky, but we rarely notice it undergoing any sort of change. This, however, is an illusion. the sun changes all the time. As science has advanced and we've been able to shield out the worst of the sun's glare, it became possible to study the sun's surface. As early as 1610, it became clear that the sun was a boiling, shifting sea of barely restrained plasma, which frequently wasn't restrained. In spite of the intense gravitational force holding it all together, the nuclear reactions taking place in its core are so hot, reaching 15 million degrees Celsius in its center, that plasma bubbles and bursts on its surface, erupting into solar flares that blaze in all directions. Sunspots, dark patches of the sun's surface that are filled with intense magnetic fields and can be between 1,600 and 160,000 kilometers across, form, drift, and vanish. Coronal mass ejections explode out of the sun's corona, the atmospheric zone above the sun that is strangely 200 times hotter than its surface. It's hard to find a place in the solar system that is as active as the sun. What many people do not realize is that that activity waxes and wanes. The sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and CMEs all become more common during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum compared to the sun's minimum, and large CMEs go from happening once every few days to multiple times in a single day. This is known as the Schwabe cycle. Interestingly, this represents one half of a larger cycle known as the Hale cycle, which maps the changes in the sun's magnetic polarity. Once every Schwabe cycle, every 11 years, the sun's magnetic north pole and south poles swap places. When another Schwabe cycle occurs, the poles swap back. Tick, tick, tick. This constant rising and falling of solar energy levels thrums through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its rhythm. We don't really understand why the sun goes through this cycle. It's clearly related to the magnetic processes that exist within the sun itself. Yet, although we have observed these cycles in action for the last 200 years and have seen evidence of their influence on the Earth over the last 10,000, we're still no closer to figuring out why the sun cycle has a length of that particular time period rather than any other. What force drives it? Lacking any other obvious answer, some scientists have tried to connect the orbital length of Jupiter, also about 11 years, to this cycle length, but this could easily be a coincidence. Although Jupiter represents 2.5 times the combined mass of all the other planets in the solar system, and definitely exerts some gravitational pull on the sun, its orbit cannot explain the variations, seemingly random, that the sun's cycle undergoes. Much of what goes on within the sun is a mystery to us, but its influence on Earth, that is much easier to see. It begins with the space around us. Space is more and more important to modern civilization, so it shouldn't be surprising that CMEs and solar storms streaming out from the sun more regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from harmful rises in radiation levels, and it also allows the delicate hardware on satellites to be powered down to prevent that hardware from being fried. This is important, as solar radiation can cause unexpected electrical currents to form in wiring, overloading systems that haven't gone into a safe standby mode. But there's another aspect to geomagnetic storms that you might not expect. All of that radiation has an impact on the atmosphere itself. It warms it, albeit just a little. As the atmosphere warms, it expands, and this has an impact on our satellites. In space, there is no drag, so objects can orbit practically forever. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and low Earth orbit satellites have to maneuver every 2 to 3 weeks to keep from falling from the sudden friction. And this isn't always enough. In 1989, there was a geomagnetic storm that was so powerful it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly slowed the satellite down. Ironically, the mission had been studying solar flares. This is not an isolated incident. NORAD, the Northern American Aerospace Defense Command, has to relocate hundreds of satellites after each geomagnetic storm, as they have been knocked out of their old orbits. Radiation can also influence our ionosphere, filling it with charged plasma. This can have a slight lensing effect on your GPS systems, reducing their accuracy from within a meter to over 10 meters. The next time you look on Google Maps and it thinks you might be a street across from where you are, a geomagnetic storm might be to blame. Our power grids brace themselves every 11 years for the uptick in these current-inducing events to keep themselves from being overloaded. Amateur radio enthusiasts and airline pilots find their high-frequency radio range dropping significantly as radio waves get deflected or even blocked completely by the more powerfully charged ionosphere. As I predicted in my horoscope, this all adds up to some less reliable technology. The fact that the next solar maximum is expected to arrive soon, in 2025, makes me quite confident in my prophesying. There are some bright sides to this. As space weather becomes more turbulent, parts of the world such as Canada see a rise in the number of auroras dancing hypnotically across the sky. Aurora chasers report rises in sightings from a few times a year to as many as twice a month during the most energetic parts of the Sun's 11-year cycle. So much for the Sun's influence on space and our technology. You might think that that's the end of it. The Sun cycle might influence machinery, but it's not going to make much difference on anything alive, right? If you think that, you'd be wrong. It's not for nothing that the rest of my horoscope mentioned poorer health. There's growing evidence that the Sun cycles can even influence ecosystems and species themselves, including humans. Some of this is incidental. When the Schwabe cycle is at the solar minimum, the Sun exerts less pressure through its solar winds, which means, ironically, that we get less protection from our heliosphere from cosmic radiation. This form of radiation is highly energetic, but fortunately rarely makes it through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. But reaching the atmosphere is all that's needed to produce an effect. There is a theory, although still far from certain, that this extra radiation could be creating nucleation sites in the atmosphere that seed extra clouds, influencing our weather. Even if that's not occurring, during solar maximum, the space weather hitting our atmosphere can raise global temperatures slightly. As my horoscope at the beginning predicted, a warming of the weather. Not by much, it should be said, less than half a degree, and the temperature always eventually returns to where it started, but it's enough that it's noticeable to species paying attention to temperature, for instance to decide when to start the mating season. Studies of birds have shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain. It's not like birds can look at the sun to see how many sunspots there are. Nevertheless, a link seems to exist, according to the 5 nesting groups that were looked at. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope, bad health. There are numerous studies on how solar cycles might influence this. In 2011, a study spanning 2 decades of nearly 1/3 of women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The study also checked 1 man during the same period, which admittedly is a much smaller number of candidates. Still, it was interesting to note that the man experienced slight elevations in oral temperature, pulse rate, blood pressure, and respiration rate that took place soon after solar maximum too. It's not just physical. There's even an influence on the rate of mental disorders. A study in 2006 looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that, of all those clients, those born during higher energy chaotic cycles experienced an increased rate in mental disorders. If this is the case, then the cycle of the sun at the moment of your birth might just have influenced the course of your life. It's not quite star signs, but astrology might just be onto something, at least with one specific star. Ultimately, the science on this is still ongoing, and it should be stressed that any health impacts caused by these cycles are extremely minor. As one researcher put it took hundreds of thousands of patients to even notice that there was a health impact. The sun cycle should not prevent you from living your life. We're currently heading towards a solar maximum, predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was mutated to give it abstract thought and consciousness. If so, if they gave us the means to perceive the universe, we have much to thank solar maximums for. We wouldn't be us without them. What does the sun sound like? It's a simple enough question, and one that comes with a simple enough answer. The sun is silent, of course. Because sound doesn't travel in a vacuum, to us, the sun sounds like nothing at all. But let's do away with simple answers. What if sound actually could propagate through space? Without a giant cosmic muffler between us and our closest star, what would we hear? Would the sun sing to us, an enchanting melody in our sky? Or would its noise be such a cataclysmic cacophony, it would instantly be the last thing we ever heard? Scientists actually have the answer. Through spacecraft like the Parker probe, which is currently making skimming orbits around the sun, they can detect the kind of pressure waves and particles emitted by the sun and can convert those waves into the sounds we might hear if space was capable of such propagation. And interestingly enough, not all of the sun sounds are the same. I'm Alex McColgan and you're watching Astrum. Join with me today as we listen to several different sounds made by the sun, recreated through clever science, because it turns out that these sounds may allow scientists to solve 2 of the sun's greatest mysteries. In our imaginary scenario, where space has suddenly gained the ability to propagate sound, we can now start listening to the sun all the way from Earth. Although the Earth is 152 million kilometers away from the sun on average, it's perhaps unsurprising to learn that the sun is very loud, easily audible from where we are. It would sound something like this. Just a reminder, there is no sound in space. This is a sound reconstruction, turning amplitudes and frequencies into sound waves, creating clips of what the waves might sound like to the human ear if an atmosphere were present. This soothing buzz has an almost electrical feel to it. It reminds me of generators, or perhaps even something vaguely radioactive, which is appropriate given that this is the sun we're talking about. The nuclear fusion going on inside the sun is equal to 3.85 times 10 to the power 26 watts every second. About 1 million times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the sun would produce. To get a sense of what this would be like, take the device that you're watching this on and connect it up to the speakers that they use at your next rock concert. Then play this noise at full blast. At 110 decibels, this volume level is survivable for short periods of time, but would likely end up with the entire population of the planet going deaf if they weren't wearing earplugs as it plays in our sky non-stop. In fact, we can consider it extremely fortunate that we don't actually have to deal with this. Species would have probably evolved with no ears, as hearing would be pointless. If we get closer to the surface of the sun, that sound level grows exponentially, with some experts rating it at 270 decibels. Remember, decibels are a logarithmic scale, so every 10 decibels higher it goes, you have to multiply the sound level by 10. To get a sense of how loud this would be, 270 decibels is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 decibels in Earth's atmosphere, as different mediums have different volume caps, due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the sun would be 100 million times higher than this cap. The sun is loud. Which is a shame, as some of the sun's sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the sun has reached us, many of the sun's sounds have blurred into one, meaning we miss out on some of their fascinating intricacies. To gain a better insight into the sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the sun for now, and instead let's focus on its sound patterns. If we were to enter a spacecraft and head towards the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas to date. You see, it's tempting to think of this stream from starting inside the sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, an important discovery had been made through observation. Although particles within the sun's atmosphere, or corona, were moving around with an average speed of 145 meters per second, particles outside of the corona were traveling at 618 meters per second. This meant that particles that had enough speed to escape from the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma too. It is far too hot. Although you might expect the center of the sun to be the warmest part of it, and the temperature to gradually go down the further from the center you go, this stops being true once you enter the corona. The surface of the sun has an average temperature of 5,600 degrees Celsius, but within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees Celsius. Something in the sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It's here that we would meet the third sound of our tour of the sun. As our spaceship would draw closer and we passed over the boundary between the corona and empty space, something known in science as the Alphen surface, we would begin to hear the following. These are known as Langmuir waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, a magnetic equivalent to the sound a kettle makes when it boils. We have entered one such stream. Countless of these streams fire out from the sun's surface. The sun's exterior is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star's mass along the island's edges, and something about this process of rising and falling material, or something going on within the sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by the magnetic force and is sent streaming into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Langmuir waves is eerily beautiful. As the winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds, as faster parts of the wave run ahead while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already travelling ahead. Eventually, this evens out into the hum we heard at the beginning. There is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications. Here, right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away if you have the right detectors. To truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles, nothing too special. Now, here's what they sound like on the sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly, all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that roar is being caused by, but at least one theory for the force behind this sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Magnetic reconnection sounds fairly innocuous, and yet its innocent, technical-sounding name disguises a cataclysm. The sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart. I cannot stress enough how powerful these are. When magnetic field lines travel away from the sun, it's sometimes possible for them to merge with other field lines, causing some of those iconic loops to form that you've likely seen in images of the sun before. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc, there's a massive realignment in the excess field line's polarity. Everything above the arc needs to find a place to go to ensure magnetic equilibrium is maintained. Cut from their tethers, the field lines further out from the sun form an arc of their own, which then catapults off into space like the releasing of a gargantuan stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to be able to even see nanoflares, and aren't entirely certain the nanoflares they've seen are indeed the hypothesized events they were expecting, although they do seem to be accompanied by the expected superheating. This is an explanation that is still being worked out. Most of it is not yet understood. And still, it's not completely far-fetched that such moments when the sun gets so wound up it snaps explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system with quite the force we witness. Although, to go from a single crack into the roaring wail that we hear, and to account for the constant solar wind travelling outwards in all directions from the sun, nanoflares, or whatever the force behind this phenomenon is, must be extremely widespread throughout the entire corona. The sun continues to hold many mysteries. The Parker Solar Probe, which collected many of these sounds, continues its journey around the sun, gathering valuable data with every pass. The Parker Probe is only 4 years into its 7-year mission, so hopefully it will collect plenty more information for scientists to pore over. Perhaps they will find more sounds for us, each one a clue to the ancient riddle of how the universe works. Because ironically, just like listening to the ticking of a clock to try and figure out how the clockwork functions, the secrets to the sun might one day be solved by what we hear rather than by what we see. It is something hardwired into humans to want to be remembered. For thousands of years of mankind's history, people have erected monuments to themselves and performed great deeds, all to endure after they'd passed on. It's no wonder some people might want to be the one who made a great scientific discovery, like discovering a special star or a planet, so they'll be remembered for all time. However, being overzealous could lead to being remembered for all the wrong reasons. I'm Alex McColgan and you're watching Astrum, and in today's video we're going to be looking at the fascinating discovery of a planet in our solar system closer to the sun than Mercury. It was observed dozens of times by various astronomers. The only problem? It doesn't actually exist. Let's rewind to the year 1846, when something astounding had just happened in the scientific community. Aubin Jean-Joseph Le Verrier, a French astronomer and mathematician, had just helped discover the planet Neptune using nothing but pure mathematics. He had been examining the rotation of the then 7 planets when he noticed that something was off about Uranus. It didn't seem to be moving in line with the theories of gravity proposed by Newtonian physics. Le Verrier reasoned that the only explanation for this was that there must be a planet out beyond the orbit of Uranus that was perturbing its motion to account for this discrepancy. He did some maths and then declared that his 8th planet must exist at an exact point in the night sky. The incredible thing was, after hearing his prediction, Le Verrier's friend Johann Gottfried Galle got out a telescope, searched in that location, and sure enough discovered the planet Neptune in a single hour. It was almost exactly where Le Verrier had predicted that it would be. The scientific community went wild with this discovery, and Le Verrier was rightly celebrated for his incredible deductions. So it's not surprising that a decade later, when he predicted the location of a 9th planet using the same methodology, the scientific community listened. In fairness, he had not been the first to predict that such a planet existed. It was as far back as 1601 that German astronomer Christoph Scheiner had claimed to have noticed a strange black spot moving in front of the sun, and had claimed that this was a planet. In reality, it was most probably a sunspot. Other alleged sightings had been made throughout the years. Capelle Loft in 1818, Franz von Greuthuysen in 1819, J.W. Pastorff between 1822 and 1837 all claimed to have seen an object or objects orbiting the sun. Pastorff claimed to have seen it at least 12 different times. People had even begun to spitball a name for this hypothetical planet. In 1846, French astronomer Jacques Babinet suggested calling it Vulcan, after the Roman god of volcanoes, fire and metalwork. This would have been an appropriate name, as any planet closer to the sun than Mercury would have been exceptionally hot. Mercury already experienced temperatures of 427 degrees Celsius. Vulcan would have been even hotter. And yet, for all these sightings, confirmation of the planet remained elusive. But what made Le Verrier's claim stand out was the way he had come to make it. In 1845, before his discovery of Neptune, Le Verrier had been asked by the director of the Paris Observatory to apply Newton's laws of physics to the orbit of the planet Mercury to see if the two lined up. Leverrier did so, laying out a theoretical orbit that Mercury would take around the Sun based on Newtonian physics. Once his prediction was made, astronomers observed Mercury to see how well it matched up. Only it did not. Leverrier tried again. Reasoning that it was possible his maths had been out, he did a much more thorough study in 1859. Using multiple observed sightings of Mercury as his baseline, he once again mapped out Mercury's orbit. But once again, his predictions were out. Not by much, only 45 arcseconds per century, but enough that there was conclusively something weird going on. Confident of his maths this time, Leverrier reached the conclusion that there must be some mass pulling Mercury out from the idealized orbit, either a planet or a series of asteroids. Given his success by now at locating Neptune, many astronomers believed him. Scientists rushed to telescopes to try and spot the alleged planet, and it wasn't long before results began to come in. Spotting a planet so close to the Sun was inherently difficult. The glare of the Sun would completely obliterate the reflected shine of a tiny planet. As such, the most effective method of spotting such an object was to see the darkening it caused as it travelled across the Sun. And in 1859, Edmond Modeste Lescarbot claimed to have seen just that. Lescarbot was a French amateur astronomer and physician who, using basic tools in a homemade observatory, claimed to have spotted a small black object passing by the Sun on the 22nd of December. He wrote to Leverrier, who was so taken by his claim that he travelled by train to the man's home unannounced to verify it. He questioned Lescarbot, heard his observations, and came to the conclusion that the man was telling the truth. So the two of them announced to the scientific community Lescarbot's discovery. They named the planet Vulcan. The scientific community was once again very impressed. Lescarbot was given the Légion d'honneur, the highest order of merit in France. He got to speak at meetings of learned scholars. There was only one problem. The planet he had discovered didn't actually exist. There were numerous proofs of this. For one, naturally, other scientists wanted to take a look at this new planet Vulcan. Leverrier calculated from Lescarbot's observations that Vulcan must orbit 21 million kilometers out from the Sun and did so every 19 days and 17 hours. So it would be easy to spot, as it would be calculable when it would pass the Sun again next. Astronomers pointed their telescopes towards the Sun at the appointed time, but Vulcan was a no-show. Leverrier was troubled by this, but by then more reports were coming in of the planet's sighting. Other astronomers were going back through their records and were matching up phenomena they had seen with the new planet Vulcan. Some of these were years out of date and not even listed as to when in the year they had happened, but Leverrier still used these to tinker with his model, reasoning that perhaps his maths were just out. So he would predict and would not see Vulcan, and would rework his theory and would not see it again. Another piece of damning proof came from Emmanuel Liais, another French astronomer. Liais claimed that he had been coincidentally looking at the Sun at the exact moment Lescarbot had, with a twice as powerful telescope, and had not seen the planet Lescarbot had claimed to have observed. Vulcan's existence floated through murky waters, as there were renowned scientists who did claim to see it from time to time. Leverrier died in 1877, but just a year later in 1878, two well-renowned astronomers both claimed to have seen Vulcan at the same point in the sky at the same time during a solar eclipse. They even both claimed that the planet was reddish in color. The corroboration was compelling, yet Vulcan still did not exist. In science, if a fact is true, then it is repeatable. And in spite of all these observations throughout the years, Vulcan was never repeatably observed. It was never seen during a solar eclipse again. In time, that corroborated sighting was put down to calculation errors and misidentifying a known star. But ultimately, the one who finally put the idea of Vulcan to rest was Albert Einstein, and he did so by thinking of something completely different. Numerous scientists over the years had attempted to see Leverrier's planet Vulcan because mathematically they were certain it had to exist. Newtonian physics demanded that it did. They strained to see it, and in that confirmation bias, they did see it again and again, just never in the same place. But Einstein realized that it was Newtonian physics that was at fault. In 1915, he proposed a model of physics that accurately described the motion of the universe, but relied on things like curvature of space-time rather than gravity. At slow speeds, it looked a lot like Newtonian physics, but when you placed objects like Mercury next to very massive objects like the Sun, special relativity predicted a different path for their orbits. And sure enough, Einstein's model predicted the exact orbit that Mercury made around the Sun, deviations and all. And with that, the case for Vulcan's existence evaporated. Under special relativity, it couldn't exist. There could be no object next to the Sun of a planetary size, or it would mess with Mercury's orbit so that it would no longer line up with the maths. And this time, Einstein was able to prove his maths correct through tests like the Eddington experiment. There is a lesson in this somewhere. Sometimes if we want something too much, we find it regardless of whether it is really there or not. Sometimes it takes thinking outside the box and challenging our previously held beliefs before the truth can be found out. As scientists, and equally as lay people, it's important that we do not hold too tightly to our ideas. The truth does not need our fervor. It will prove itself, given time and opportunities for repetition. So, there you have it. The planet Vulcan, a planet of fire that was nothing but smoke and mirrors, a yearning for something, but never a reality. Newtonian physics were replaced by Einstein's theories of relativity, and now special relativity is here to stay. At least until it is supplanted by something even more comprehensive too. Have you ever looked up at the sky and seen something so strange it made you wonder if you were dreaming? Perhaps you saw what looked like a rainbow, only it was upside down. Or maybe you saw a perfect circle of light around the sun with 2 splashes of rainbow color on the sides. Well, no need to pinch yourself. What you are seeing is a unique category of optical phenomena called ice halos. Although similar, they aren't technically rainbows, but their own distinct wonder. Some are relatively common, while others are extremely rare. As you might know, rainbows occur when sunlight is refracted by water droplets suspended in the atmosphere. When light travels from one transparent substance to another, such as from air to water, its speed changes, bending its path and separating the light into colored bands by wavelength, a process called dispersion. But what happens when light hits water particles that are made of ice rather than liquid water? Well, depending on the shape and orientation of the ice crystals, as well as the direction of the light hitting them, they can produce a whole range of optical phenomena. To date, 119 kinds of ice halos have been categorized, and there might still be others we don't know about. So what are ice halos? How do they form? And what should you look for if you want to see one for yourself? And finally, are they a sign of something more ominous on the horizon? I'm Alex McColgan and you're watching Astrum. Join me today as we look at spectacular images of some of the better known ice halos and get to the bottom of how and why these delicately beautiful spectacles appear. This stunning photograph shows a 22-degree solar halo spotted over Großkrotzenburg, Germany. 22 degrees doesn't refer to air temperature, but to the angular radius of the halo. To visualize this, imagine drawing a direct line from a point on the halo to the observer's eye. Then do the same from the sun at the circle center to the observer's eye. The angle between these two sight lines is 22 degrees. Hence the name 22-degree halo. There are also 46-degree halos, which, as you might guess, are larger than their 22-degree cousins, but are also fainter. Halos can also occur in moonlight, as you see here. These eerily beautiful halos are called moon rings, or winter halos, but they're technically the same optical phenomenon. What distinguishes them from solar halos is the source of light. In some images, you may notice that the patch of sky inside a halo appears darker than the sky outside the ring, a dramatic effect that is sometimes described as a hole in the sky. This happens because, when light bounces and refracts off the ice crystals, none of it is reflected toward the light source, which, to an observer, leads to an apparent darkening inside the halo. But this is just the tip of the iceberg, because ice halos take on all kinds of strange and shocking forms. Spots of vibrant color, upside down rainbows, and even upside down rainbows at night. But before we get there, let's take a moment to break down the fascinating optics that produce these strange occurrences. Most circular halos are made by water crystals in cirrus or cirrostratus clouds. These clouds occur high in the troposphere, usually 5 to 10 kilometers above the Earth's surface, where temperatures are very cold. As a result, halos can be seen anywhere on Earth all year long, even in very hot climates. Atmospheric ice crystals are small, usually less than 10 micrometers long, and uniform in size and shape. This extreme regularity has to do with the structure of ice on a molecular level, and is necessary for making halos. You see, water molecules consist of 2 hydrogen atoms and an oxygen atom. In liquid water, the bonds between hydrogen atoms are weak, so the bonds are constantly breaking and reforming as the molecules slip past each other. But when water freezes, that molecular movement slows to a halt, and the bonds between hydrogen atoms become fixed. This results in a hexagonal lattice structure known as a tetrahedral arrangement. This highly organized structure on the molecular scale is what causes the ice particles to form hexagonal crystals. Some crystals are flat, like plates, whereas others look like columns with a hexagonal cross-section. Despite this variation, these crystals behave so uniformly because of their interfacial angles. In fact, the angles between any 2 faces of ice crystals are completely identical. It's this extreme regularity of the interfacial angles, rather than the crystal's mass or shape, that allows millions of particles to scatter the light with the consistency needed to produce a halo. Halos are sometimes quite colorful. That's because when ice crystals refract light, the red and blue frequencies bend at slightly different angles and disperse. Some 22-degree halos have 2 colorful spots visible to the left and right of the sun. These beautiful looking phenomena are called parhelia, or sundogs. Sundogs appear when ice crystals that are shaped like hexagonal plates take on a horizontal orientation. As I mentioned earlier, some crystals form as thin hexagonal plates, whereas others form as columns with hexagonal cross-sections. When plate-shaped crystals form and settle downward, atmospheric drag orients them horizontally, with the c-axis you can see pictured almost perfectly perpendicular. Larger plates tend to wobble just a bit more than smaller ones. This wobble, in turn, affects how tall sundogs appear to be, with wobblier plates causing the sundogs to appear more vertically stretched. Sundogs are sometimes accompanied by another optical phenomenon called a circumzenithal arc. These arcs look similar to rainbows, only they're upside down, which gives them a friendly, smiling appearance. These arcs appear over the sun only when the direction of light and the orientation of the ice crystals are just right, when light enters the top faces of hexagonal plate crystals and exits the side faces. However, this can only happen when the sun is lower than 32.2 degrees above the horizon and more than 5 degrees. Because the ice crystals function essentially like a 90-degree prism, the color separation is excellent, meaning circumzenithal arcs have a far higher degree of clarity than actual rainbows. And if you're really lucky, you might even spot one with moon rings. Called lunar circumzenithal arcs, these unusual arcs only appear when the moon is extremely bright and fairly low on the horizon. As strange as it sounds, it is possible to see what looks like an upside-down rainbow at night. Now, This is amazing. Circular halos have also been sighted on Mars. Here is an image taken by Perseverance on the 15th of December 2021. This has led some to suggest that the cause may be carbon dioxide crystals in the planet's cold, thin atmosphere, or perhaps a mixture of CO2 and water ice. We didn't always know that halos occurred on Mars, so as you can imagine, the Perseverance team was pretty excited to see this. Because the size and appearance of the halos provide clues about the types of crystals forming in the atmosphere, scientists hope that studying halos here on Earth and spotting them on other planets could shed light on the composition of those planets' atmospheres. As a result, more research will be undertaken in the future to document and understand the appearance of ice halos on Mars, as well as other moons and planets. So there you have it, a primer on some of the better known ice halos and their associated optical phenomena. And if you want to see one for yourself, here are some things to look for. First, check for cirrus clouds. These are the high altitude, wispy clouds that contain the small ice particles needed to produce ice halos. Second, look for the sun or moon, but take care not to stare directly at the sun, kids, because that can damage your eyes. While rainbows form around the anti-solar point, which is located directly opposite the sun in the celestial dome, most ice halos form in proximity to the sun or moon. And while ice halos tend to appear in fair weather, they often arrive at the front of an approaching storm system. Meaning, if you see one, it's better not to linger outside for too long. Head indoors and find somewhere cozy to enjoy the upcoming storm. So, if the weather is fair, but you see rain in the 24-hour forecast, keep an eye on the sky. Your chances of seeing a halo will be higher. Of course, the best way to see one is to look every day. Ice halos can form anywhere on Earth, so if you keep looking up, you're bound to see one sooner or later. But when it comes to ice halos, there's plenty more to talk about. There are a lot of other strange and even rarer kind of halos, and probably more yet to be discovered. So if this is a topic you'd like to see more about in the future, and if you've seen them for yourself, I'd love to hear about it in the comments. The Solar and Heliospheric Observatory, also known as SOHO, recently celebrated its 25th anniversary in space. During these 25 years, it has observed the solar wind, watched out for dangerous coronal mass ejections, and observed the atmosphere of the Sun. An unintended consequence of its observations around this region were the discovery of over 4,000 sun-grazing comets, most of which we had no idea existed until they came into SOHO's view. And SOHO isn't the only solar observatory. The Stereo spacecraft and the Solar Dynamics Observatory have all seen new comets. And what's so cool about that is that they weren't designed with that in mind at all. I'm Alex McColgan and you're watching Astrum, and in this video I wanted to look at some of the most impressive of these comets, try to understand how they interact with the Sun and how the Sun interacts with them. Sun-grazers are comets that do just that. They graze the Sun as they pass, with the closest parts of their orbits taking them within a hair's breadth of the Sun's surface. Often they will pass through the Sun's huge atmosphere, called its corona. These comets are mainly long-period comets, comets whose orbits take hundreds to thousands of years to complete. Because of their orbit's extreme elliptical nature, they build up tremendous speeds as they approach the Sun, sometimes accelerating to 0.2% of the speed of light, an absolutely incredible speed for a particle, let alone a house-sized object. The majority of sun-grazer comets actually all originate from one large comet that was ripped apart several hundred years ago. This group of sun-grazers, shown in red in this video, is known as the Kreutz sun-grazers. What tends to happen over time is that the fragments from the larger comets spread out, meaning that there is probably a steady flow of them. As the largest of these comets also pass by the Sun, they too break apart into even smaller comets. And the reason we believe most sun-grazers originate from the same comet? Well, they all tend to follow the same orbital path. The brightest comet in the last millennium, known as Comet Ikeya-Seki, was probably a fragment. It was so bright as it approached the Sun that it could even be seen during the day. You may have heard of another famous fragment of this comet that dimly illuminated the sky in the southern hemisphere in 2011, called Comet Lovejoy. While Comet Lovejoy wasn't as bright to the naked eye, it did make for some very impressive long exposure images and was seen by all the Sun observing satellites. Comet Lovejoy was not expected to survive this encounter, as it would have been in the Sun's 1 million degrees Celsius corona for more than 1 hour. However, astonishingly, it fizzed away from the other side of the disk, mainly intact, although probably severely impacted from the experience. The same thing happened to another comet, Comet Ison. You may remember that Comet Ison was expected to be a bright comet, potentially visible to the naked eye when it passed by the Sun in 2013. Alas, that wasn't to be. However, it still made for good viewing for the Sun observing satellites. Ison's approach was bright and impressive, and upon reaching the other side of the Sun, it faded out. Scientists can't be sure if the nucleus survived or not, but if it did, there are certainly no volatile substances on it anymore. All that's left is probably dust. However, these are some of the biggest Kreutz sun-grazers we've ever observed. Their nucleuses maybe being a few hundred meters in diameter. Some of the smaller comets were not known about until they actually came into the view of a Sun-observing satellite. Due to their small size, being only tens of meters across, many of the smaller comets were completely snuffed out by the Sun immediately after passing by too closely. Which means unfortunately, they were vaporized pretty much immediately after they got discovered. Sometimes they will pass around the back of the disk of the Sun, never to re-emerge from the other side. Although at other times, the angle of the comet's orbit means we can witness this vaporization as it happens. At this distance from the Sun, the heat is incredible and the gravity is overwhelming. The icy comets not only evaporate quickly, but the rocky elements of them are also ripped apart from tidal forces. Our own close encounters with comets show that they tend to be structurally weak and very porous, sometimes nothing more than a pile of rubble held together by its own gravity. So combine that with the influence of the Sun, and even the largest sun-grazer comets will come away heavily scarred. Now, there's an interesting phenomenon that happens when a sun-grazer passes by the Sun, and that is that a CME will go off at the exact moment the comet passes by. There are numerous examples of this. However, scientists are still of the opinion that there is no mechanism for a sun-grazer to cause a CME. These comets simply aren't big enough to have any consequential impact on the Sun, so it is currently believed that these examples you see here are purely coincidental. What scientists enjoy about sun-grazers though, is that while we can't send probes deep into the Sun's corona, it's simply too hot for that, we do have these thousands of comets that are willing to take the plunge for us. And comets are perfect for us to observe what we are looking for, which is to better understand the magnetic fields within the corona, so that we can better predict CMEs and space weather generally. Look how as a comet passes by, its tail wiggles. The particles in the tail get heated so much they turn to plasma, which can easily be seen by the UV cameras of the satellites. Plasma reacts strongly to magnetic fields, so the wiggle you see in the tail is believed to be due to the way in which the tail interacts with the magnetic field lines in the corona. Currently, space weather is something we don't have a complete understanding of, so as more comets pass through, the more we will begin to understand that environment. So there we have it, some of the most impressive looking sun-grazers caught on camera by satellites that weren't even designed for them. Have you ever been fortunate enough to see a comet? What was your experience like? I'd be interested to hear your stories in the comments below. Have you ever wondered what it would be like to have two suns in our sky? Seeing two suns during a sunset would be a spectacular sight indeed. And actually, it isn't such a rare occurrence. It is currently estimated that a third of star systems have two or more stars. Which made me wonder, how much would having a second star impact us here on Earth? How hot would Earth get? What would the day and night cycle be like? Would it be possible for life as we know it to survive in a multi-star system? Well, it depends. Let's keep our Sun as it is and only make the second star the variable in this thought experiment. As we know, stars come in all sizes, from small, cool and dim red dwarfs, all the way up to large, hot and bright blue supergiants. In a binary star system, the stars orbit around the system's barycenter, or the center of mass. Depending on the mass of the star and the distances between them, you'll have differences in how these orbits look. For similarly sized stars, the orbit could look circular in nature, or in an ellipse. On the other hand, the bigger the discrepancy there is between the star's masses, the closer the barycenter will be to the more massive star. Let's say we plonk a red dwarf, which is the smallest star type, in a close orbit around our Sun. Even though a red dwarf can be as little as 7.5% the mass of our Sun, it's already going to have a big impact on us. From our perspective, the star would look like it orbits the Sun, meaning there would be times when it transits in front of the Sun, and other times where it is eclipsed by the Sun. Our year would be shorter if we stay 1 astronomical unit from the system's barycenter. Because of the increase in mass and gravity of the system from the extra star, Earth's velocity would have to be faster in order to not be pulled into the stars. Either that, or its orbit would have to be slightly further out if we wanted to maintain our current velocity. The increase in temperature from the star would be noticeable too, definitely making it unbearable for humans. But exactly how hot would depend on a variety of factors, like a runaway greenhouse effect, the heat of the star, and more. But let's say we place Earth's orbit in such a location that we can survive. Seasons would still be massively impacted, as the tilt of the planet would be secondary to the distance to the second star. When the second star is as far away as possible, and the hemisphere on Earth was also experiencing winter, it would get extremely cold. On the other hand, combine a summer with the second star passing as closely as possible, and it will be incredibly hot. Additionally, a curious phenomenon with red dwarfs is that they also produce huge flares, much larger than the ones our Sun produces. They would easily knock satellites offline on a regular basis, and Earth would have some spectacular aurora. Our power grid as it stands would also be under serious threat from these stellar flares, as they would act like hemisphere-wide EMP bombs. The interactions with this second star could well make our Sun more active too, meaning it too may produce more flares. So even with the smallest type of star, our habitability on Earth would be under serious threat. Increase the mass of the second star, and you'll start to get additional problems, like increased UV radiation, making going outside more and more dangerous. You'll also have 2 shadows a lot of the time. Once you turn the second star into something like a blue supergiant, there really won't be a place in the system where there is even a hope of habitability. Blue supergiants can be many times the mass of our Sun, the theoretical limit being 150 solar masses. Their volume is also big. They make the Sun look almost puny in comparison. They can be millions of times more luminous than our Sun too, with devastating stellar winds, enough to rip our atmosphere off over a relatively short time frame. Larger again are yellow supergiants and then red supergiants. While not as massive or as luminous as blue supergiants, red supergiants are the biggest stars in existence. If you plop the largest known of these stars directly into the center of our solar system, not only would they easily encompass Earth, but it would encompass everything up until Saturn. That's 10 billion times the volume of our Sun. However, there is a scenario where we could be in a binary star system with a supergiant and still be on a habitable planet. You see, binary stars can orbit very far apart, taking thousands of years to complete one orbit. The most extreme cases can see a binary star system with a separation of over 1 light year. And what can happen is that planetary systems form around each of these stars separately, meaning that if Earth was in one of these planetary systems, it would only have the one parent star, even if that star was part of a binary. The second star would be easily visible in the night sky, but may not make much of an impact during the day, depending on its luminosity. Stellar winds from the other star would have little impact on Earth, as our Sun's powerful magnetic field would redirect most of it away. The big problem with a supergiant on your doorstep is that it is a ticking time bomb. Supergiants tend to be on the verge of erupting in a supernova. A supernova going off only 1 light year away would be catastrophic, probably sterilizing the entire planet as radiation from the shockwave passes over. And that's not to mention the gamma ray bursts from the resulting neutron star. In fact, a recent study has suggested that being within 50 light years of a supernova going off would be close enough to be catastrophic in nature. However, the good news is that we don't know of a star capable of erupting in a supernova within 100 light years. Going back to the single parent star binary star configuration, on Earth with a single sun, we have a set day and night cycle. However, should we have a second sun outside of our orbit, but still pretty close to us, it's going to mess with that day and night cycle pretty badly. There would only be tiny parts of the year where you would get a proper day and night cycle, and as the year progresses, you would get less and less of a night until at one point where you'd have no night at all. So, there we have it. While having a second sun during a sunset seems like it could be an amazing prospect at first glance, delving into the details reveals that we are extremely lucky to only have the one sun. No matter what configuration you look at, there are some major problems with the second star, be it devastating solar flares, a ruined day-night cycle, having a neighbor that might explode at any moment, having our orbit completely eaten up by the volume of the star, huge swings in seasonal temperature changes, having our electronics fried out regularly, UV radiation, and likely more that I haven't mentioned. In reality, even if life as we know it does exist around binary star systems, they have some major obstacles to overcome to get to where we are now. So let us be grateful for our boring but steady and safe star, the Sun. Long may it continue to be so. Often, on a clear day, I will briefly glance at the Sun and be in awe about how big and bright it is in our sky. It's hard to think that it's millions of kilometers away, yet it has such a massive impact on us here on Earth. Life would be impossible without the Sun. Almost everything can be traced back to the light and energy it provides. Even though it's relatively close to us and not exactly hard to spot, there's still a lot we don't know about it. Which is why both NASA and ESA have sent spacecrafts to study the Sun in the last 2 years. These missions will be the closest we've ever been to our star, so close in fact that they will be able to directly interact with its atmosphere. So why are we sending these spacecrafts to the Sun? What will they do there? What have they found so far? And what makes each of these missions special and unique? I'm Alex McColgan and you're watching Astrum. And in this video we will investigate NASA's Parker Solar Probe and ESA's Solar Orbiter and how they will explore our own magnificent star, the Sun. The Parker Solar Probe was announced in 2009 and was launched on August 12, 2018 on a Delta IV Heavy rocket. It will use 7 Venus flybys over nearly 7 years to gradually shrink its orbit around the Sun. At its closest point, it will only be about 6.16 million kilometers away, which is inside the Sun's corona, or its atmosphere. Being that close would feel like 500 suns in the sky beating down at the same time, with the temperature reaching up to 1,400 degrees Celsius. The spacecraft is going 7 times closer to the Sun than any spacecraft has gone before, and at these temperatures, many components that are used to make sensitive equipment for spacecraft would melt away. To protect the spacecraft and all its equipment, it is shielded by an 11 centimeter thick carbon composite shield, which can withstand these high temperatures. This shield also has a white reflective surface that can help minimize heat absorption. The shield will always be facing the Sun, protecting the spacecraft in this harsh environment. Being far away from Earth and orbiting a very dangerous object, this spacecraft is, by necessity, as autonomous as a space mission has ever been. Because the heat shield always has to be facing the Sun, For large sections of its orbit, it won't be able to point its antenna at Earth. During these times of communication blackout, it will control each of the sensors, control the formatting of data products, and archive high-resolution data until it can communicate with Earth again and transmit back what it has captured. ESA's Solar Orbiter mission began development in 2012, and after 8 years, the Solar Orbiter was launched on February 10th, 2020 on an Atlas V rocket. The Solar Orbiter will also use gravity assist from Venus as well as Earth. These swing-bys will put the Solar Orbiter into an initial 180-day orbit around the Sun. The spacecraft will reach the closest approach to the Sun every 6 months at around 43 million kilometers away. This is comparatively much further away than the Parker probe's closest approaches, but just to give you an idea of the temperatures at this distance still, at 43 million kilometers from the Sun, the temperature can reach up to 500 degrees Celsius, as the sunlight will be 13 times more intense than what we feel on Earth. The Solar Orbiter is protected by a heat shield made with titanium foil layers about 40 centimeters thick, which is not as effective as the Parker probe's heat shield, but still enough to protect the spacecraft on its dangerous mission. It is surprisingly difficult to get a probe into a close orbit around the Sun, as it takes 55 times more energy to go to the Sun than it does to go to Mars. You see, the Earth is always moving sideways relative to the Sun at very high speeds, about 30 kilometers per second or 108,000 kilometers per hour. In order for a probe to successfully enter into an orbit around the Sun, it must cancel out almost all of that motion. This is why both the Parker and Solar probes were launched using two of the most powerful launch vehicles available at the time, the Delta IV and the Atlas V. The objectives of the Parker Solar Probe and the Solar Orbiter are similar to a great extent. Both these missions aim to find out more about our Sun's corona, its solar winds, coronal mass ejections, the structure of the Sun's magnetic field, and simply how it all fits together. The Sun, like all stars, is a ball of plasma. Plasma is superheated matter, so hot that the electrons are stripped away from the atoms, leaving an ionized gas. The Sun has an atmosphere of extremely hot but tenuous plasma extending out for millions of kilometers called the Sun's corona. You can see the plasma atmosphere in this image, although typically it is far harder to see than the Sun itself, as the Sun's outer layer, known as the photosphere, is much brighter. The ideal time to spot the Sun's corona is during a solar eclipse, when the Moon blocks out the photosphere disk, leaving just the wispy arms of the corona visible. The strange thing about the Sun's corona is that its temperature is between 1 million and 3 million degrees Celsius, whereas the Sun's surface temperature is only about 5,500 degrees Celsius, and currently we don't really know why. And while the Sun's corona looks substantial, its brightness is deceiving. It is actually magnitudes less dense than Earth's atmosphere. The Sun continuously releases huge amounts of plasma and radiation into space, which is known as the solar wind. Solar wind is not very strong or dense, and the Earth's magnetic field diverts most of it harmlessly away. While a lot of solar wind does get redirected around the planet, some gets funneled towards the planet's poles, where ions from the solar wind collide with atmospheric oxygen and nitrogen atoms, the interactions of which emit the beautiful colors we see in auroras. The number of particles ejected by the Sun is not constant. Reconnection events in the Sun's magnetic field can release huge amounts of energy in the corona, ejecting millions of tons of charged particles into space in one big eruption. This is what is known as a coronal mass ejection, or a CME. When these CMEs interact with the Earth's magnetosphere, it causes what's called a geomagnetic storm, and the biggest of these storms can be devastating. The largest geomagnetic storm ever to hit Earth was the Carrington event back in 1859. If such a CME was to hit Earth now, the resulting storm could affect satellites and our electric power supply in what could be described as a hemisphere-wide EMP bomb. As we depend on electricity and the internet so much, even a few hours of outage could cause serious problems. Some estimates show that if a Carrington-sized event happened today, it could cause a few $1 trillion in damages. And unfortunately, CME flares are fast. They've been shown to reach Earth in just 17 hours. This might not be enough time to alert the entire population, turn off reactors, and take necessary precautions. In reality, we have simply been lucky up until this point, as we missed a Carrington-sized event hitting us by a margin of 9 days in July 2012. Had it been 9 days later, Earth would have been a bit further in its orbit and in the CME's path. This is why it is so important for us as a delicate species to understand the Sun's corona so we can better predict solar storms, to give us better warning and hopefully avoid damages associated with a Carrington-sized event actually hitting us. It's just a matter of when rather than if. Now, these two probes may seem similar, and while a lot of their goals do overlap, they both have some unique features. The Parker probe is going deep into the Sun's corona, where no man-made object has gone before. Because it has to withstand such high temperatures, the spacecraft is limited in some ways. For example, it cannot take pictures of the Sun, as no current camera technology could look directly at the Sun from that close and survive. But the Parker probe has instruments that can directly sample and collect data about the particles that exist in the Sun's corona, and even closely study the regions where solar winds originate, something that can't be done at a distance. The Parker probe is lighter, smaller, and has less equipment compared to the solar orbiter. The solar orbiter, on the other hand, carries both particle detectors and telescopes. It can take close-up pictures of fascinating solar landscapes, and due to its orbit, it will be able to track a region of the solar atmosphere for much longer than is possible from Earth. This will enable it to observe storms building up in the atmosphere over several days. So, as you can see, these probes are complementary, and both will help further our understanding of the Sun's corona in their own way. So, what have these missions achieved so far? Well, on the 27th of September 2020, the Parker probe passed within 13.5 million kilometers of our star, the closest any spacecraft has ever been. Also, it became the fastest traveling human-made object ever, traveling at 466,000 kilometers per hour. And this isn't even as close or as fast as it's going to get. Still, even at this distance, the data sent back from the Parker probe is already helping our understanding of how the Sun's magnetic field and the corona interact to form solar winds. The probe also discovered that some magnetic fields from the Sun sweep through the solar atmosphere, which can increase the solar wind speeds by as much as 500,000 kilometers per hour. In addition, it has discovered evidence of a dust-free zone 5.6 million kilometers from the Sun. It's believed this is due to the vaporization of cosmic dust particles by the Sun's radiation. The solar orbiter has already sent back its first images of the Sun, and scientists found something called campfires, which you can see here. These are explosions on the Sun's surface that occur as a result of disturbances in small magnetic fields. The solar orbiter also took the closest images in existence of the Sun's surface from 77 million kilometers away. And the examination of particles across its orbit will help us understand the different types of space weather. The Sun is a giant, bright celestial object of intense nuclear energy. It unleashes billions of tons of electromagnetically charged plasma hurtling into space every day. These violent eruptions, called coronal mass ejections, or CMEs, shoot off into the solar system, causing what we know as solar storms. These highly charged plasma particles race towards Earth at over 1 million kilometers an hour. And one might think that with the speed and intensity of these particles, we should all head for the bunkers when they arrive. However, the Earth has natural protections in place to prevent most of these particles from hitting us. One such protection is the Earth's powerful magnetic field. which pushes the particles around the planet and to its poles. Particles that do hit the atmosphere are absorbed and provide the energy to drive the climate on our planet. In fact, the sun is crucial to life on Earth. For example, it provides just the right amount of warmth and light so that plants can photosynthesize the sun's energy to usable carbohydrates. This energy makes its way down the food chain until it reaches us, humans. We eat and convert food to give us energy that our bodies can use. Almost all food energy can be traced back to the sun, our life giver, and the very beginning of our food chain. But could the solar system's giant also create catastrophe? How big can these CMEs get? What if the largest solar storm of all time was to hit Earth tomorrow? Could the sun actually damage or destroy humanity? For a star, our sun is relatively stable, a type of star informally known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our sun is as stable as it is, as unlike most other stars, the energy it emits is fairly constant. If you were to look at footage of the sun taken by the Solar Dynamics Observatory, however, you would quickly realize that even one of the most stable types of star has a landscape of activity. Sunspots, solar flares, and coronal loops are present every single day on the sun's surface. Could say the surface almost appears to be fluid, but the sun is neither solid, liquid, or gas. It is rather a giant, nearly perfect sphere of plasma. It is composed of mainly hydrogen and helium, and at the center of the sun, due to its enormous mass, nuclear fusion takes place. At the sun's core, hydrogen atoms are fused together under immense pressure to become helium.
The sun itself, I tend to think of it as an onion, basically consisting of different layers on the layer. So in the core, in the very center of the sun, essentially that's where nuclear fusion happens. Now you have to think, so essentially the sun is a kind of huge ball of plasma, soup of particles, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon to travel through the radiative zone something like 170,000 years. It's basically it's that dense.
And then from that, it then hits the convective zone. So everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom near that radiative zone, and then it expands and it rises to the surface, and that's the main transfer of heat from that point onwards. Obviously then glowing from the surface like any hotter material does.
Plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields.
So sunspots are actually the surface representation of the magnetic fields of the sun. So the magnetic fields actually get very tangled below the surface. So between that radiative zone and the convective zone, the magnetic fields get tangled.
They tend to appear in pairs, in groups. If you think sort of a magnet, you have positive polarity, negative polarity. That's sort of normally what we see in sort of in sunspot pair. One would be positive, the other would be negative. And normally the strongest magnetic fields that we observe are in the sunspots.
The sunspots can be anywhere from about 15 kilometers in size to around about 160,000 kilometers, so multiple times the size of the Earth.
Sunspots can often be seen at the base of various solar phenomena. Coronal loops, large rings in the Sun's atmosphere. Prominences, large, bright, gaseous features extending outward from the Sun's surface, reaching into space for thousands of kilometers. And solar flares, a sharp increase in the Sun's brightness and temperature.
Solar flares tend to happen over active regions, and active regions are essentially sunspot groups. So these are the locations where we definitely see the strongest flares.
So a reconnection event is essentially what produces the energy that causes both flares and CMEs.
Because the convective zone is very turbulent, many of the sort of current simulations show that most of the magnetic field as it rises through the convective zone is basically being destroyed, being diffused around. It's more complicated magnetic structures, such like twisted magnetic fields that tend to survive. And so you can imagine, especially sort of over large sunspot groups, we do see very complex magnetic field configurations, magnetic fields, twisted, wreathed, basically creating these complicated geometrical topological structures. And it's within that structures that magnetic fields, the magnetic energy is stored. And what happens during reconnection? I tend to describe it, think of the magnetic field as a rubber band. So you twist it, turn it, and then basically at some point you pull it too strongly and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event? Essentially, as the name suggests, the magnetic field lines reconnect.
And when that happens, you get a lot of energy being released. Of the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares, where large amounts of radiation is released, and also it will potentially lead to large-scale movement of the material that was suspended in the prominences, both towards the Sun and away from the Sun. When that reconnection event happens, then again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the Sun, often following those magnetic field lines, so moving to the footprints, like for instance, move to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the Sun. And so what you'll end up having is millions of tons of charged material flying out from the Sun relatively fast. Of the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, coronal mass ejections.
These CMEs come in contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of the atmosphere by the force of the ejection. This leaves the planet with just the heavier molecules, a toxic smog that cannot, as far as we know, sustain any life. Earth would have a similar fate if it wasn't for its relatively strong magnetic field. Particles from a CME aimed at Earth are redirected around the planet because of the Earth's magnetosphere. Some particles get redirected to the Earth's poles, where the charged particles hit the Earth's ionosphere, causing beautiful aurora. Thanks to a combination of the Earth's magnetosphere and atmosphere, we are totally protected from all sorts of particles space likes to throw around. Or are we? When the Earth is hit by a CME, this is called a geomagnetic or a solar storm. When a solar storm hits us, Earth's magnetic field gets somewhat compressed by the force of the CME for the duration of the storm. Normally this wouldn't and hasn't been a problem for people with their feet firmly on land. But what would happen if the most powerful solar storm ever recorded was to hit Earth today? To find out what is believed to be the most powerful CME in recorded history, we have to go back to 1859 to a solar storm known as the Carrington event. From the 28th of August to the 2nd of September 1859, many sunspots appeared on the Sun in one place. On the 29th of August, southern aurora were visible as far south as Queensland, Australia, which implies a solar storm was occurring. Before midday on the 1st of September, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson wrote reports independently, which were both later published in scientific journals. The flare was connected to a major coronal mass ejection that traveled directly towards Earth, taking 17.6 hours to make the 150 million kilometer journey, much faster than the speed of normal CMEs. Typically, a CME would take several days to reach Earth. It's thought that the high speed of this one was made possible by a prior CME, perhaps the cause of the large aurora event on the 29th of August in Australia, which would have cleared any ambient solar wind plasma for the Carrington event like a giant slipstream. With this slipstream in place, the way was set for the biggest CME known to man. On the 1st to the 2nd of September 1859, the largest recorded geomagnetic storm occurred. Aurora was seen around the world, all across the northern hemisphere, as far south as the Caribbean. The aurora over the Rocky Mountains in the US was so bright that the green glow woke local gold miners, who began making breakfast as they believed it was morning. It was reported that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was visible as far from the poles as Sub-Saharan Africa, Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very close to the equator, such as in Colombia. This is unprecedented, as typically aurora aren't visible at the middle latitudes. By the 3rd of September, the aurora in the sky was said to be the brightest and most brilliant it had ever been. However, although beautiful, this storm brought unforeseen problems. A consequence of the geomagnetic storm was that the electrically charged particles from the Sun surged telegraph systems all over Europe and North America, which caused them to fail, even in some cases giving the people that operated the telegraph equipment electric shocks. Telegraph pylons threw sparks from the charged atmosphere. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so strong that it compressed the magnetic field of Earth all the way down to its atmosphere. Due to the fact that North America and Europe were facing the Sun at the time, these areas of the world were most affected from the initial cannonball of the CME. Looking back at geomagnetic storms since the 1850s, There have been a few which were big, but not devastating. For example, in March 1989, a CME hit Earth, rendering satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was knocked out for about a day. Some people there incorrectly thought the Soviets were attacking, and the glow in the sky was the result of nuclear bombs. Thankfully though, this solar storm and many like it did no lasting permanent damage. Today, if a CME the size of the Carrington event or bigger was to hit Earth, the consequences would be far more disastrous than they were for mankind in the 1800s. Technology was only just picking up back then, whereas today we have satellites in space, computers, telecommunications, power plants that would all be severely damaged in such an event. Due to the range of a solar storm, it would greatly impact equipment over a large area, the most susceptible technologies being the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for a lengthy period of time. If transformers did get damaged, for example, it would take years to replace, as transformers take years to manufacture. Often, these transformers are tailor-made for the specific requirement and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be down as fuel stations require electricity to pump, replacing that food would be problematic. Payment systems that rely on credit cards would not work. People would not have access to the internet as computers would not have power, and battery-powered devices would run out quickly. Radio and TV stations would be disrupted. Hospitals would struggle when the backup generators ran out of fuel. We would be completely cut off from the outside world. The world is simply so dependent on technology, and especially on electricity. It is feared we have lost the ability to function as a society without it. And worryingly, it is our power grid that is most vulnerable to a super solar storm. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion, ultimately destroying the economy. And unfortunately, that does not cover the social impact it would have. As is often the case in natural disasters, some people would undoubtedly resort to more primeval instincts, with attitudes such as every man for himself. Chaos, looting, and disregard for the law could occur. This would only get worse the longer the population goes without hearing from their government or organization of authority. Hopefully, in such a situation, the good of mankind would prevail, but it is a possible scenario. The think tank placed the estimated recovery time to repair the damage of a CME at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation, disease, and chaos during that time. We only need to look at a couple of examples to understand the severity of the situation. In 1989, Quebec experienced a large solar storm that made the power grid fail in just 90 seconds. This problem was exacerbated by the fact it was winter, where the temperature can drop well into the minuses, which left vulnerable people in a potentially bad situation. It took 9 hours to restore power, and total costs from the disruption were estimated to be around $2 billion Canadian dollars. From the social aspect, we only need to look at Puerto Rico, which is still without power for 40% of its population from the time of writing this script in early February. That means it has been without power for 140 days,
and is estimated that it still needs 50,000 utility poles and roughly 10,000 kilometers of electricity cables. If a solar storm hits, it wouldn't just be an island that is rendered powerless, it would be an entire hemisphere, and Earth has had some very near misses. A Carrington-size event could have been a reality in 2012, where a huge CME was ejected from the Sun. This was the biggest CME that has been recorded with modern technology, and it directly hit one of the stereo satellites that was observing solar activity. It is the charged particles that cause this distortion effect shortly after this solar flare. And had it hit Earth, the hypothetical disaster scenario could have become a reality. Due to lack of historical evidence, we have no way to predict when the next big CME could hit Earth. As far as we know, a CME even bigger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. But what mitigation plans does the world have in case of such an event? Since 1995, NASA have placed a telescope in orbit which is constantly monitoring the Sun for CMEs. As light travels much faster than the speed of a CME, it would roughly give us about 17 hours warning before the CME hit Earth. If everyone was acting fast enough, this might be enough time to turn off some of the power stations, thus protecting the electricity grids. This is called the Solar Shield Program, and astonishingly, the US is currently the only country to have such a program in place. Countries are also working on temporary transformers, which are quicker to produce. Additionally, countries throughout the Western world are currently in the process of proposing upgrades to the power grids that would not allow a surge of electricity caused by a geomagnetic storm to destroy the network. This process, however, is slow and bogged down by bureaucracy. It seems countries are in no rush to foot the bill to upgrade the infrastructure. These measures to protect the power grid are not already in place worldwide. It also seems that most people in the world are not even aware of CMEs, but rather fear much less likely scenarios like an asteroid hitting Earth or aliens invading. Mankind as a whole is shockingly unprepared for a natural disaster caused by a super solar storm. George H. Baker, Professor Emeritus from James Madison University, spoke before the House Committee on National Security in the United States and gave this explanation for the reason progress is not getting made. He said, "To a major extent, the lack of progress in protecting our most critical infrastructure to solar storms is that the responsibility is distributed. There is no single point of responsibility to develop and implement a national protection plan. Nobody is in charge." When I asked the North American Electrical Reliability Corporation about EMP protection, they informed me, "We don't do EMP, that's a Department of Defense problem." The Department of Defense tells me EMP protection of the civilian infrastructure is a DHS responsibility. DHS explained to me that the responsibility for the electric power protection is within DOE, since they are the designated sector-specific agency for the energy infrastructure. And this is sadly from one of the most progressive countries in the world on the subject. And until mankind is prepared for a CME, we really are at the mercy of our life-giver star.
It doesn't take much to learn that the Earth is facing an energy crisis. Fossil fuels are finite, but also represent 80% of the source of our electricity. At some point, we will inevitably run out, whereupon we will either need to get our energy from somewhere else or brace ourselves for the shocking reality of a world without machinery, computers, and phones. If the idea of pushing a plow all day in an agrarian society doesn't quite align with your life goals, then you'll be in favor of the alternative, finding a different energy source for most of society's energy needs once all the oil, coal, and gas runs out. You've likely heard of options like wind, geothermal, or tidal power. But do these approaches dream big enough? Could the answer to the energy crisis actually be something that sci-fi writers have been talking about for over 60 years? Although it's a long way off, could humanity actually build a Dyson sphere one day? And just how far off are we from being able to do this? I'm Alex McColgan, and you're watching Astrum. Join me today as we examine the case for Dyson spheres and discover how the maths behind these gargantuan structures might make them not just possible, but actually plausible for our future energy supply. I was recently going through an online course when I came across the topic of Dyson spheres, and they really caught my imagination. Dyson spheres are crazy. They were first explored in a paper by British-American theoretical physicist and mathematician Freeman Dyson, who was considering the way hypothetical alien civilizations might try to power their society and how we might spot them. All life requires energy to live, and the more advanced a society, the more energy it seems to end up needing. Dyson thought that if an alien race was spacefaring, they might build a habitat in space near their local star to take advantage of its solar radiation. Over time, more and more habitats would be built, until one day, most or all of the star would end up surrounded by a truly mammoth shell of habitats, which would capture and utilize all the radiation the star was emitting. This shell was eventually considered one single structure and came to be known as a Dyson sphere. Creating one would give a species access to a ridiculous amount of energy, sending their civilization into the next stage up in galactic exploration and expansion. Dyson got the idea after reading a science fiction book known as Star Maker, something he publicly credited, and indeed, this idea does sound a little like something out of sci-fi. It would be very hard, and potentially take a very long time to build anything so large, and seems to be well beyond the capabilities of our own current civilization. That said, this sci-fi idea might need to be something we consider a little more closely. As the course I was learning from pointed out, there are just over 8 billion humans on Earth right now, and we collectively use 4 times 10 to the power 20 joules, or 400 quintillion joules of energy per year. This sounds like a lot, and it is, particularly when you consider that the current estimated amount of remaining energy available in oil reserves is 6 times 10 to the power 22 joules, or 60 sextillion joules. Doing a little division, it becomes clear that we only have 150 years of oil reserves left if we continue burning it at our current pace. 150 years is really not that many. And given how quickly we are ramping up energy consumption globally, it's fair to assume that we might run out of oil sooner, even if more oil reserves can be found. I talk a little more about this subject in another of my videos here. Which is why finding another mass source of energy, such as utilizing the energy available in sunlight, actually is quite appealing. Compared to what we gain from fossil fuels, the sun produces a staggering amount of energy, even if you're only considering the amount of light that hits our planet's surface directly. Let's use a little equation to show you what I mean. At this distance, the energy we receive from the sun is around 1,360 joules per squared meter per second. Multiply this across approximately 1.1 times 10 to the power 14 square meters of the sun's circular area as it cuts through space, then multiply this again across the course of a whole year, all 31,536,000 seconds of it, and we would receive around 4.7 times 10 to the power 24 joules of energy. That's 10,000 times the energy we are currently using from oil. More than enough to cover our needs, assuming we could harness it. Obviously, capturing all that sunlight is a bit tricky to do in practice, And obviously, if we were to capture all of it, that would make life a bit difficult for any plants on the planet wanting to use that light for photosynthesizing purposes. But even if we got to the point where we were only using half of all that available energy, we would completely remove our need for fossil fuels and could have the energy necessary to support a significantly larger population at the same time. Forget 8 billion, we could sustain 40 trillion people here on Earth. At which point, the biggest problem wouldn't be how to give all those people the energy you'd need to sustain their lifestyles, but where to put them all. Increasing the population density by 5,000 times would go from there being on average 7 people per square kilometer to being 35,000 people per square kilometer, or 1 person per 3 square centimeter. So making this work might be a bit of a challenge without some creative housing plans. Regardless, this does seem like a good solution to the energy crisis. The joules are there. So if we can already cover our population's needs by fully accessing only a small fraction of the sun's total output, the part hitting the Earth, we probably don't need to harness any more of it just yet. However, looking to the future, that won't always be the case. Reaching 40 trillion people is actually not that far off, at least on the scale of human history. Our population is currently growing at a rate of 0.88% a year. At times this number has been as high as 2%. For simplicity, let's just take a nice round 1% figure and calculate using that. If we increase for the population size by 1% every year, the cumulative growth of the population would hit 8.8 billion in a decade, 22 billion in a century, and 40 trillion in only 800 to 900 years. So what might be the solution when that happens? Why, doing as Dyson's hypothesized alien races do, and increasing the amount of solar energy that we capture, probably by building solar panels or mirrors and sending them into orbit around the sun. As the course I was learning from highlighted, with more solar collection tools comes more benefits. A Dyson sphere, or a Dyson swarm, as this segmented configuration is technically known as, offers power that's many orders of magnitude higher than what we can do with just a planet's worth of surface area. Harnessing it would elevate us to a higher level of civilization, one that went from controlling its planet to harnessing its entire solar system, perhaps giving us the springboard that could truly kickstart our expansion across the stars. On the Kardashev scale, a method of measuring a civilization's advancement by evaluating how much energy they could potentially use, this would tip us from a Type 1 civilization into a Type 2. In case you're wondering, we're currently only about a Type 0.7, as we've not quite managed to make use of all the energy on the planet, while a Type 2 would have access to all the energy in the solar system. To get to a Type 3, we'd have to harness the entire galaxy, so that's a long way off. Still, the energy levels a Dyson sphere could produce are already so extravagant, it seems silly to our current understanding to even contemplate them. If we completed a Dyson sphere, or a Dyson swarm, we would go from 4.7 septillion joules to 10 decillion joules, increasing our energy levels by 20 trillion times. That should be enough to keep the lights on for the foreseeable future. Technologically speaking, we are pretty much at the point where we could make a solar panel that could capture sunlight from the sun and send it towards Earth, or even easier, we could simply create space mirrors to reflect the light towards where we needed it, say an orbiting space foundry outside of Earth's atmosphere, with the same end result. This might be the simpler idea, as then you don't have to worry about how to transfer all the generated electricity from the solar panel back to Earth. You can just send the sunlight directly to wherever it's needed, although you would be sacrificing some habitability on the Dyson sphere itself. Placing mirrors into stable orbits is not impossible for us, and having them be able to maneuver slightly to reorient through the year doesn't sound too implausible. So then it's just a question of how much materials would this require. Unsurprisingly, depending on what distance you created your shell, a Dyson sphere would need a lot of material. For instance, the course I was learning from identified that building a Dyson sphere that coincided with the Earth's orbit would need about 6% of the entire volume of the planet, even if the panels were less than a millimeter thick. This is hardly ideal, even if we could selectively drill out the materials that were needed. But if we instead built a sphere at a much more compact distance from the Sun, say at the distance of Mercury's orbit, then the material requirements become much more feasible. Mercury itself contains all the raw material that might be needed for such a structure. And as far as we know, there is no one living on Mercury who would complain if we were to fill it with holes. But then, the last issue to consider, other than the moral question of whether it's okay to tear apart an entire planet purely for our own benefit, is that it's obviously an energy-intensive process. Materials have to be mined, processed, then made into their components. The solar panels or mirrors would need to be built, and even once that's done, they need to be lifted out of Mercury's gravity well. And that's a particularly energy-intensive process. If we utilized all the sun's energy that was hitting the planet Earth and spent it all on doing nothing but lifting mirrors for our Dyson sphere out of Mercury's orbit, we can calculate how long it would take us to lift enough mirrors to complete the entire shell. We know the formula for overcoming the gravitational binding energy of Mercury, which for Mercury gives us roughly 2 × 10 to the power 30 joules. We already know how much energy we at maximum could get from sunlight here on Earth, 4.7 × 10 to the 24 joules. So then it's just a simple matter of dividing the first by the second. And voila! This process would only take a measly 425,000 years, during which time there would be no energy left to support Earth's population or give light to our plants, because we're using it all to build a Dyson sphere. Maybe this isn't such a viable idea after all. But wait, there's one last point to factor into this. That's the fact that once our mirrors came online, they could start providing energy of their own to help pay the energy costs. This would then become an exponential process, with no additional input required from Earth, perhaps except for a little oversight. One mirror would provide energy to make a second, then both would double to make 4. Every instance you would be doubling your number of mirrors, and once you get exponential growth involved, depending on how much energy you put into the system at the start, the entire thing could be completed much sooner. According to some calculations, Mercury would be completely disassembled in as little as 31 years. In other words, if we started building one right now, you might live to see its completion. Ethical considerations aside, such numbers really bring into focus the viability of this project. Something that takes half a lifetime to complete is certainly ambitious, and the initial cost might indeed be great. There would be some practical considerations to think about in terms of the best way to set up mining operations on Mercury, but these are questions we're already putting our minds to anyway. Scientists are currently working out how to set up bases on the Moon with similar intentions. We're not far away from doing the same on other planets once we have the techniques down. In other words, there really aren't very many barriers left towards attaining the immense energy of the Sun. A Dyson sphere might well be another example of something that sounded like science fiction to us, but will turn out to be something our children or grandchildren will one day come to take for granted. In the middle of the day, the sky starts to darken. It's as if dusk has fallen early. People look and notice something is happening to the Sun. A dark shadow moves before it, gradually devouring every last trace of brightness until our familiar light bringer is only a shimmering, ghostly ring around a pitch black orb. A total eclipse is occurring. This will soon be a reality. One is coming to the continent of North America in April 2024. But If, like me, you are one of the many billions of people who won't get a chance to see that particular solar eclipse this April, you might be glad to know that America is not the only place they happen. And neither is Earth. Have you ever wondered what a solar eclipse looks like on another planet? Wonder no more. I'm Alex McColgan and you're watching Astrum, and today we're exploring solar eclipses, but not just the ones that happen here on this planet. Allow yourself today to feast your eyes on the actual images and even videos NASA has taken of spectacular eclipses from various places around the solar system. Firstly, I'll quickly explain some of the terminology to do with eclipses. A total solar eclipse is when an object moves in front of the sun, completely obscuring it, also known as an occultation of an object. This is the typical kind of eclipse we see on Earth, when, at certain points in Earth's orbit, the orbit of the moon aligns with the sun. There is something special about an eclipse here on Earth, and I'm not just saying that out of some Earth-focused pride. By a bizarre but highly fortunate cosmic coincidence, the moon is the right size and distance from us that its angular diameter is almost identical in size and shape to the angular diameter of the sun in our sky. This leaves for an impressive spectacle where the corona of the sun, or in other words, the sun's upper atmosphere, creates a ghostly aura around the moon. This corona, normally too dim to see, extends for hundreds of thousands of kilometers into space. Looking closely around the edge of a total solar eclipse, and you will also see the silhouette of the moon's craters along the outside, plus these reddish wisps coming off from the sun. These are prominences, millions of tons of charged particles suspended in the sun's atmosphere by powerful magnetic fields. During an eclipse here on Earth, the moon casts a shadow about 250 kilometers in diameter, which moves across the Earth as the moon orbits. In the case of the eclipse happening this April, this shadow will arrive at the Mexican west coastline, then will make its way up through the United States until it passes into parts of Canada, before moving over the ocean once more. You can see on this map the path the shadow will take. If any of you happen to live in its pathway, or are close enough to make the drive, you may want to try and see this eclipse for yourself. The sun will only be totally obscured within the diameter of this shadow. Outside of that, the sun is only partially obscured from the viewer's perspective. This viewer is witnessing an annular or partial eclipse, also known as a transit. The shadow moves across the Earth extremely fast, at roughly 1 kilometer a second. Witnessed from a high altitude, it is a majestic sight as the shadow shifts across the landscape. Satellites have also witnessed the movement of this shadow. The shadow isn't as sharp as you might expect, and this is due to the angular diameter of the sun and the moon and their distance apart. The sun itself is huge, a whopping 1.4 million kilometers across. The moon is much smaller, at only 3,400 kilometers across. Now, this image isn't to scale, but it shows visually why the shadow isn't sharp. The umbra is the shadow where the sun is completely obscured, and the penumbra is the shadow where the moon only partially obscures it. This part of the shadow is much wider than the 250 kilometer wide umbra shadow. So why doesn't the moon create eclipses every month when it orbits in front of the sun? Well, this is because the moon's orbit is not in line with the Earth's orbit around the sun. This means there are only a couple of times per year when the alignment is right. This alignment of 3 celestial objects is known as a syzygy. A very cool word, but not something you'll need to remember for this video. I just thought you would find that interesting. If you live in the UK like me, sadly you won't get to see much of the eclipse this April unless you live at the furthest west parts of the country, as the sun will be dipping below the horizon just as it begins. Maybe we will get to see some devil's horns though. Still a spectacular sight indeed. But the Earth is not the only place to experience solar eclipses, and we have the images and videos to prove it. Let's explore eclipses of our closest celestial neighbor, the Moon, because it would make sense that if the Moon can occult the Earth, then surely the Earth can occult the Moon. And the answer is yes, but it's not the shadow that's the really visually appealing part of this, from the Earth anyway. This is because the Earth is 4 times as big in the Moon's sky as the Moon is on Earth's, so when the Earth fully obscures the Sun, the whole Moon is in the umbra. At first, the shadow of the Earth creates a crescent shape. Explain that, flat earthers. But what is different this way around is that, unlike the Moon, the Earth has an atmosphere. This means that when the Moon is totally eclipsed, the Earth's atmosphere refracts the Sun's light around the planet, gently illuminating the Moon in a reddish hue. This makes for a beautiful but almost spooky view. The color is caused by Rayleigh scattering, a topic I've discussed in another video. Rayleigh scattering is the same process that makes our sky blue and our sunsets red. This image is beautiful in that you can see the different wavelengths of light being scattered through Earth's atmosphere, from deep red from this side through to blue on this side. From the Moon's perspective, none of the Sun would be visible during a total eclipse, but the atmosphere on Earth would be illuminated, so you would see a ring around it. This is an actual view of a lunar eclipse on the Moon by one of the JAXA probes in 2009. It's quite the awe-inspiring sight. The Earth and Moon aren't just getting in the way of each other either. Here is the Earth eclipsing the Apollo 12 spacecraft in 1969 while it was on its way back home. And here's the Moon getting in the way of the Earth from the perspective of the Discover satellite. Interestingly, this is the side of the Moon you never see, as the Moon is tidally locked to the Earth, which means the same face is always looking towards Earth. From this perspective, the Moon looks very foreign, but it is indeed a real video of our only natural satellite transiting the Earth. From another satellite's perspective, but this time looking at the Sun with the SDO satellite, the Moon often makes an appearance. The position of this satellite as it orbits the Earth means the Moon can block the Sun occasionally. And here's the Moon again, this time from the perspective of one of the stereo satellites. The Moon isn't the only thing that orbits between us and the Sun. Mercury often transits across the Sun, a tiny minnow compared to the solar system's giant. The next time this will happen is on the 13th of November 2032, so a little while away. You might want to put it in your calendars for now. Venus also orbits between us and the Sun, and as it is much closer to us and bigger than Mercury, its silhouette appears much larger. Its last transit was in 2004 and 2012, but sadly if you miss those two, chances are that you will never see it. These transits happen in pairs, and then there is a 100-year gap until the next one. In other words, the next transit will be in 2117. This happens for the same reason the Moon doesn't eclipse us every month. The orbits just don't often align. Still, we have high-definition videos of the last one, and it is quite the sight to behold. Moving to another planet now, we can go to Mars, which has plenty of unmanned robotics either in orbit or on the surface. Mars also has 2 moons, Phobos and Deimos. They are both pretty small. Phobos is 22 kilometers across and Deimos is only 13 kilometers across. They both orbit very close to the planet though. Phobos is only 9,000 kilometers above the surface and Deimos is 23,000 kilometers, which means although tiny, you can still easily see them from the surface of Mars, especially Phobos. The Curiosity rover was able to capture a moment where, incredibly, Phobos eclipsed Deimos. This video is captured in real time and shows the size differences of the moons in the Martian sky. And this is not all the Curiosity rover captured. It was also able to see a transit of Phobos in front of the Sun. Due to the distance of Phobos to Mars, it moves across the sky fairly quickly, only taking about 7 hours to orbit once. This means that this video you are watching is in real time, and these solar eclipses on Mars don't last for more than about 30 seconds. The surrounding ground does get noticeably darker during an eclipse by Phobos, as can be seen from the rover's perspective, but it can also be seen from space. Phobos' shadow here can be seen by the Viking 1 orbiter, and also here more recently by the Mars Global Surveyor. The Opportunity and Spirit rovers have also seen a transit of Deimos, but it appears much smaller, just a dot passing in front of the Sun. It doesn't cause a noticeable decrease in brightness. Mars is pretty impressive, but that's not all the solar system has to offer. Have a look at this video captured by the Hubble Space Telescope, looking at Jupiter. Jupiter has 4 large moons, 3 of which at certain points can transit the planet at the same time, leaving 3 big shadows. The moons in question in this video are Io, Callisto, and Europa. Interestingly, like we talked about before with the Umbra and Penumbra, you can see that because Io is the closest to the planet, its shadow is the sharpest. Whereas you can see with Callisto, the furthest away of these 3 moons, the Penumbra is much larger, causing a blurry shadow. And in this video, Hubble spies the occultation of Ganymede, the largest moon of Jupiter. Cassini saw some incredible transits and occultations of Saturn's many moons. Here is one of Epimetheus passing in front of Titan, with Dione coming in from the side. This little white dot coming in from the left just under the ring is in fact a bright background star. And this Hubble view is magnificent. Here are Enceladus, Mimas, Dione, and Tethys orbiting Saturn. Once every 15 years, Saturn's rings and moons are aligned just right so that the moon's shadows stream across the rings as well as on the planet. This video is a time-lapse that lasted 9.5 hours. Amazing. Going a bit further out, we come to Neptune and its biggest moon, Triton. Sadly, we don't have a video, but this image captured by Voyager 2 is gorgeous. 3 days after passing by Neptune, Voyager was able to capture the crescents of Neptune and Triton before Neptune slipped in front of Voyager's view of Triton. Going further out again, we come to the furthest celestial object explored in the solar system, Pluto. As New Horizons whizzed by Pluto in 2015, it turned its camera back towards Pluto to capture the dwarf planet totally eclipsing the Sun. What it saw was dazzling. The sunlight streaming through and illuminating the atmosphere and its haze layers, with the ridges and mountains on Pluto's surface highlighted by the stark contrast of Pluto's night side. Occultations and transits may be breathtakingly beautiful, but are they actually useful to us scientifically? Well, did you know that Uranus was discovered to have rings because of an occultation of a background star? As the planet passed in front of the star from our perspective, the star dimmed before and after the planet obscured it. With this information, we are able to count how many rings Uranus has. On top of that, the transits of exoplanets in front of their stars are actually how we can detect exoplanets. Telescopes like Kepler and TESS measure the brightness of stars in the sky. If a star dims, it could be because one of its planets just passed in front of it. If the star continually dims in a pattern, for instance once every 100 days, then we know that a planet orbits that star and takes 100 days to do so. Using this method, space agencies like NASA have discovered over 3,000 exoplanets, more than all other methods of exoplanet detection combined. It can even help scientists calculate the size of the planet by measuring how much the star dimmed, or the composition of that planet's atmosphere by looking at the spectra of the light that passes through from the star to us. It might be some time before we see a solar eclipse again. After the one in April, the next eclipse won't happen in America until 2044. Here in the UK, the next one won't occur until 2090. If I live to see it, I will be a very old man. But I'm amazed as I see all of the images of eclipses that take place throughout the solar system. There's a special beauty to each one of them, a fleeting moment where one celestial body brushes lightly against another, even if it's only through their shadows. Rather than harbingers of doom, these moments fill me with awe and remind me how connected the universe is. Even across thousands, millions, or even billions of kilometers of space, we can notice a planet's passing. And if you're in the right place at the right time, oh, what wonders you can see. Earth has a pollution problem. There are plastics and landfill items, the types of things you might throw out at home. And then there's dangerous industrial waste, like nuclear byproducts, biohazards, and chemical toxins. These stifle ecosystems and affect the health of vulnerable communities the world over. So far, the best solution we could come up with for disposing of nuclear waste is burying it deep underground. Not ideal when you consider that the stuff remains dangerously radioactive for tens of thousands of years. So why don't we just strap it to a rocket and blast it into the sun, like launching a missile at a target? Wouldn't that solve all our problems? I'm Alex McColgan, and this is Astrum Answers. A big thanks to all of our patrons for making this series possible. If you want to send us your questions, join our Patreon by clicking the link in the description below. To begin answering our question, it's actually really hard to crash anything into the sun. Let's take a closer look. Suppose we've gathered together a massive pile of toxic waste destined for the sun. The first thing we'd need to figure out is how to get it into space. Easy, right? We've been launching stuff into space for the better half of a century. To get our trash pack through the atmosphere and out past Earth's orbit, we need to accelerate it to a velocity of 11.2 kilometers per second. This is the speed known as the escape velocity, where the kinetic energy of the payload surpasses Earth's gravitational potential energy. Once free of Earth's orbit, our garbage craft is on course for solar collision, right? Wrong. Once our package escapes Earth's orbit, it's still gravitationally bound to the Sun. Put super simply, Earth and everything on it is moving sideways relative to the Sun at 30 kilometers per second. Combining this sideways motion with the gravitational pull of the Sun is what keeps us locked in an orbit. If the Sun were to somehow lose its gravitational pull, we'd fly right past it at 30 kilometers per second and keep going. If we on Earth were to lose our sideways motion, we'd only be influenced by Sun's gravity and fall straight into it. So there's hope for our garbage ball yet. How could we lose our sideways motion to make this solar freefall happen? Well, there's two options. The first option is to bring up enough fuel to brake in space. Now, technically speaking, you can't really brake in the vacuum of space, but the next best thing would be to configure our garbage payload's propulsion system to generate thrust opposite to its direction of sideways motion. This cancels out the sideways motion, slowing the spacecraft down and letting the Sun's gravity do its thing. Earth orbits the Sun at 30 kilometers per second. So to brake a garbage rocket launched from Earth, you'd need to be able to accelerate 30 kilometers per second in the opposite direction of its movement. Here's where it gets weird. The closer you are to the Sun, the harder it is to crash into it. Let me explain. The closer you are to the Sun, the faster your orbital velocity. Mercury orbits at a dizzying 48 kilometers per second, while Pluto cruises at a cool 4.7 kilometers per second. The faster your orbital velocity, the more you'll need to decelerate to free fall into the Sun. That's why it is actually much more fuel efficient to fly to the outer solar system, decelerate, and free fall into the sun from there. It's not inconceivable to accelerate a spacecraft 30 kilometers per second. NASA's Parker Solar Probe accelerated beyond 176 kilometers per second, making it the fastest man-made spacecraft ever. But this brings us back to the problem of fuel. To make this break and fall method work, you'd first have to launch your garbage payload into orbit with Earth, then launch the fuel for the journey into orbit. Once both pieces are orbiting Earth, you can fuel up your payload and accelerate it past Earth's orbit into orbit around the Sun. Then you'd have to use the remaining fuel to decelerate so that it free falls into the Sun. Why not launch both the payload and fuel at the same time, I hear you ask? Well, the problem is, it's simply too much fuel. For context, the Saturn V rocket that took man to the moon needed 2 million liters of fuel just to leave Earth's orbit at 11.2 kilometers per second. A mission like this would require orders of magnitude more fuel. No modern rocket technology would even come close to being able to carry the amount needed for a journey like this. Okay, so scenario 1 is out. What other options have we got? Another way to decelerate in space is with a gravity assist. Usually when we talk about gravity assists, we are thinking of the kind that slingshot the Voyager probes into the outer solar system. However, gravity assists aren't only used to speed probes up, they can also slow them down. If you were to approach a planet from behind, fly in front of it, and exit behind the planet like this, your spacecraft loses energy while the planet gains energy. The Messenger and Bepi-Colombo probes have both successfully used this gravitational assist technique to lose velocity and enter orbit around Mercury. The thing is, this takes a lot of time. Bepi-Colombo was launched in 2018 and will only arrive into orbit around Mercury in 2025. Surprisingly, its path to get there is longer than the distance between Earth and Pluto. This is because, to slow down enough, one gravitational assist won't do. In fact, Bepi-Colombo needs 9 different gravity assists to slow down enough to orbit Mercury. Similarly, crashing our garbage into the Sun is all a game of carefully calculated orbital mechanics. If we don't slow down enough, we'll be stuck in the Sun's orbit. If we slow down too abruptly, we might get caught in another orbit we don't want to be in. Okay, you might be thinking, but Alex, this is all feasible. It's hard, but it's within the realm of possibility. So why don't we just do it? Possible? Yes. Worth the time, effort, risk, and technical challenges? Probably not. Not to be a cynic, but think about what could go wrong. First of all, we're proposing packing a bunch of nuclear waste, biohazards, and plastic onto a rocket and launching it from Earth. A launch failure or explosion could be disastrous, to say the least. Even the world's most successful rocket, the Soyuz, has a 2 to 3% failure rate. I don't know about you, but when nuclear waste is at play, I don't like those odds. Even if the launch goes well, the project itself would be ridiculously expensive. So much so that no sane person would approve the budget. There are far too many other missions on the table that would bring so much more to science and humanity than a garbage disposal mission. And lastly, it would actually be easier, quicker, and cheaper, but still crazy expensive, to shoot our garbage out of the solar system toward interstellar space. It would be less fuel intensive since the acceleration required to escape the Sun's gravitational pull is 42.1 kilometers per second, just a 12.1 kilometers per second acceleration from Earth's orbital speed. So, there you have it. We don't shoot garbage into the Sun because it's super hard, super risky, and super expensive. We're probably better off being more conscious about what we consume and how we recycle it. Thanks for watching. This video was in part made possible by all the astronauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.